start a new chapter. This is chapter number 10. In the previous chapter, we have discussed the electric field, magnetic field, or the electromagnetic waves without considering the source distributions. The source distribution means charge distribution, which can be represented by rho, and the current distribution that can be represented by J. In this chapter 10, we will study the electromagnetic waves or electric and magnetic fields by considering the source distribution. So I have written this for your notes. In previous chapter 9, we discussed about electromagnetic waves, where we studied electric and magnetic fields. We studied the electric and magnetic fields without considering the source charges, the sources, such as rho, the charge distribution, and J, the current distribution. In this chapter 10, we will study how electric and magnetic field is generated when we have the source charges. So this is the goal of this chapter. In this chapter, if we have given the sources such as rho of RT and J of RT. These are the sources. This is known as the charge density, where this is known as the current density. And using these sources, how the electric and magnetic fields can be generated. And for this, we need for Maxwell's equation. Such as divergence of electric field, rho divided by epsilon naught, divergence of magnetic field, which is equal to 0, and curl of E, which is equal to minus partial B divided by partial T, and curl of B, which is equal to mu naught J plus mu naught epsilon naught partial E divided by partial T. We know about these Maxwell's equation. In electrostatic, F, we have charge if we have charges, then one can find out electric field using Coulomb law. This is obvious. In electrostatic, if we have charges, we can find out the electric field using the Coulomb's law. This is established. And if we have stationary current, then one can find out the magnetic field using Biot-Savart law. So now in this chapter we are looking for the generalization of those laws to time dependent configuration. So this is our goal here, that we are looking for the generalization of those laws, means the Coulomb law and Biot-Savart law, which have time dependent configuration. So this is our goal. E if the charge distribution and current distribution is changing with time, then what will be the electric and magnetic field? This is the point, and this is the goal of this chapter. So you can write down these things. So this is important thing, that when the charge distribution, the current is changing with time, the charge is changing with time, then what will be the electric and magnetic field? So this is the goal of this chapter, to find out these electric and magnetic fields with time. In electrostatics, we know that if we have del cross E, which is equal to 0, we know about this. and electrostatic del cross is equal to 0, then it means that the electric field will be equal to minus del with some potential, del V. And this V is the electrostatic potential. But del cross E is not equal to 0 in electrodynamics. So this is clear. In magnetostatics, we also know that which is equal to 0, the divergence of B, which is no any monopole exists in nature, then we can get magnetic field which is equal to del cross A. And here A is the vector potential. So these are the things that we already know about this. Now, from Faraday's law, this Maxwell equation number 3, this is the Faraday's law. So if we consider del cross E, which is equal to minus partial B divided by partial T, and we already know about B, which is equal to del cross A. Then if we put the value of B in this equation, then this will be equal to del cross A. And if we write this equation in this form, del cross A divided by delta T, which is equal to 0, then we can write this equation as partial A divided by partial T, which is equal to 0. Now, this term is very, very important. This term is very important, and this is a vector quantity, because this is electric field and this is the vector potential, so the whole which is equal to also a vector. Then one can say that from previous del cross E, which is equal to from the electrostatic, we know that del cross E, when this is equal to 0, then it means that the electric field which is equal to minus del V. Now this is a vector, del cross this vector, then this vector will be equal to minus del V. So using this definition, we can say that E partial A divided by partial T, which is equal to minus del V. So using the same definition I have used. And here, if we find out E, this will be equal to minus del V minus partial A divided by partial T. And this is the electric field. And this electric field E, which is equal to minus del V minus partial A divided by partial T. And I say this is equation number first. And this is the electric field that we can find out this in electrodynamics, because this electric field is changing with time, because partial A divided by partial T. If this is not changing with time, then this part will be cancelled out. If this part is cancelled out, then we can get the electrostatic condition E is equal to minus del V. So this electric field is very, very important in electrodynamics. So in electrodynamics, we will have the electric field must be equal to this. Now, take the divergence, take the divergence of equation 1, this one. Then left hand side del cross E, which is equal to the right hand side del dot and minus del V minus partial A divided by partial T. Now multiply this divergence to this and this, then this becomes minus del square V, and this can be written out partial divergence of A divided by T. And we know about the divergence of A. We know about this divergence of E. This is equal to rho divided by epsilon naught, which is equal to minus del square V minus partial divided by partial T divergence of A. And this equation can be written out del square V plus partial divergence of A T, which is equal to minus rho divided by epsilon naught. And this equation is, we have used in this equation the Maxwell's equation third and second. We have used equation third and 2 of Maxwell's equation. And I want to write down this equation here. Now take this equation 4 of Maxwell's equation, del cross B, which is equal to mu naught J plus mu naught epsilon naught partial A divided by partial T. Putting the value of B and A, putting the values of E and B. And we know about the value of E and B, E, which is equal to minus del V minus partial A divided by partial T, and we also know about del cross A. So putting these values in this equation, then here B del cross A, which is equal to mu naught J plus mu naught epsilon naught, and the value of E must have minus del V minus partial A divided by partial T. Then after some simplification, del cross A, which is equal to mu naught J, then we have the value of this. This is minus and this is plus, so it becomes minus mu naught epsilon naught del partial V divided by partial T, and this thing minus mu naught epsilon naught partial A divided by partial T. To the left hand side, we have, this is the identity. We can use the identity to solve this term. And the identity is, previously we have discussed this identity. this may be equal to divergence of A minus del square A. So this is the identity that I have used. And further, the same things we can write mu naught epsilon naught del partial V divided by partial T minus mu naught epsilon naught partial A divided by partial T. After some simplification of this equation, it means that if I write all these left-hand terms and write down in the right, then we can get here 0. Let's say this will be equal to 0. Then we may have mu naught j, this term. This will become del square A, and similarly I can write down this term as well, minus del into del dot A, and the remaining terms remains the same. And finally, I'm so sorry, there's some mistake here. In the multiplication, this must have square and this must have square. So this is square because del divided by delta t, this becomes square, square, and square. So del square A minus mu naught epsilon naught partial square A divided by partial t square, and minus this term, one can take del square here, and this becomes del dot A minus common, this plus, then mu naught epsilon naught partial V divided by partial T, which is equal to this term go out the left side, mu naught J. So this equation we have, so we have two parts, this one and this one, and this equation. So we have the two equations that we have calculated already, where all four Maxwell's equations are used, and we have the two equations, one this and this one. So del square V plus partial this, which is equal to minus rho divided by epsilon naught, and this del square A minus mu naught epsilon naught partial square A divided by partial t square minus del divergence of A plus mu naught epsilon naught partial V divided by partial t, which is equal to minus mu naught J. These two equations are very, very important because all the four Maxwell equations we have, this is the source and this is the potential. In this equation, this is the source and this is represent this represent the potentials, because we have vector and scalar potential this side, and we have scalar and vector potential this side, and the sources are in the other side.